In the previous video, we saw that we can use the Michaelis-Menten equation, which is V naught, which remember is our initial velocity, equals V max times the concentration of substrate divided by Km plus the concentration of substrate. We can use this equation to describe the overall enzyme catalyzed conversion of an enzyme to a substrate proceeding through this enzyme-substrate complex. So in this mechanism, we said the rate determining step, the rate limiting step, is K2, the conversion of the enzyme-substrate complex into products. Since K2 is the rate limiting step, then we know the rate of this reaction, which let's go ahead and call it V, is equal to K2 times the concentration of the enzyme-substrate complex. So this is our rate law, governed by our rate determining step. Vmax, we said, occurred when 100% of the enzyme, so E tot, is in the form of our enzyme-substrate complex. So we've maximized the concentration of the enzyme-substrate complex. Km, we said, describes the dissociation of the enzyme-substrate complex to enzyme and substrate. So Km equals the concentration of enzyme times the concentration of substrate divided by the concentration of enzyme-substrate complex. Okay, so this Km describes the affinity of the enzyme for the substrate. The lower the Km, the higher the affinity. So small kms equal high affinity. In this video, we're going to explore this equation a little bit more, but now we're going to give it a graphical context. So let's go ahead and slide down here, and I'm going to rewrite my equation. V naught equals V max substrate concentration divided by Km plus the concentration of the substrate. So experimentally, what we would do is we would vary the concentration of substrate, and we're going to measure initial velocities. And based on this equation, as the concentration of substrate increases, we should expect to see an increase in our initial velocity. And that's exactly what we see. As the substrate concentration increases, so does the velocity of the reaction. However, this differs from traditional chemical kinetics because at some point we actually reach a maximal velocity. So this curve can no longer continue growing. V naught cannot continue growing even though we're increasing the concentration of substrate. And the reason for that is because we know that we have an enzyme that's important. So the first step in this is forming the enzyme-substrate complex. Since we only have a limited amount of enzyme, right, we said that E tot equals the concentration of enzyme plus the concentration of the enzyme-substrate complex. Since the concentration of the enzyme-substrate complex is limited by the total enzyme concentration, there has to be a maximum velocity. When we've reached the maximum velocity, 100% of our enzyme has a substrate bound to it. Okay, so the overall rate of this reaction is limited by the amount of enzyme that we have. And we can see that on our graph here. So this point where we've reached a maximum, this velocity is our Vmax. Okay? From this graph, we can actually also determine our Km. So if we go down to a point on our y-axis where the velocity is 1/2 of the Vmax, at this point, the concentration of substrate is the Km. So Km equals the concentration of substrate if V naught equals Vmax divided by 2. So this is really useful because it will allow us to look at a plot of substrate concentration and initial velocity and very quickly estimate the Vmax and the Km. And these are the two really important kinetic parameters that we want to be able to get so we can understand how efficient the enzyme is. So let's go ahead and scroll down here and let's explore this equation a little bit more in terms of basic kinetic ideas. So we said that V naught equals V max times the substrate concentration divided by Km plus the concentration of our substrate. Okay, and we know that we have this graph that looks like this. So we have V naught versus the substrate concentration. Okay, and it takes this shape. All right, so let's think about two different situations here. The first situation is when the concentration of substrate is much, much smaller than our Km. Okay, so if on our plot here we estimate V max to be here, so that's V max, this is V max over 2, so then this would be our Km. So in situations where the substrate concentration is much lower than Km, so we're way down here, what can we learn about the kinetics of this reaction under these conditions? So to answer this question, let's go ahead and look at the Michaelis-Menten equation and note here that on the bottom, right, so on the bottom here, we have Km plus the substrate concentration. Well, under these conditions where the substrate concentration is much, much, much lower than Km, then Km plus something that's really small is essentially 0. So the denominator of our Michaelis-Menten equation really collapses to just Km. So what we're left with is Vmax over Km times the concentration of our substrate. Okay, so what we can see here, right, so Vmax and Km are both constants. Okay, so what we observe is that the rate of the reaction, the velocity of the reaction, is directly proportional to the concentration of the substrate to the first power. Okay, so we have our rate equals a constant times the concentration of a reactant to the first power. So under this condition, when the substrate concentration is a lot smaller than Km, this is a first order reaction. So the kinetics we observe follow all predictions we would make based on a first order reaction. Okay, so this part of our graph we see first order. Alright, so let's think about a different condition. So what happens if the substrate concentration is much, much greater than Km? Okay, we're going to take the same approach here. So we're going to consider the denominator of our Michaelis-Menten equation, but in this case, Km becomes 0, so we're left with V naught equals V max times the substrate concentration divided by the substrate concentration. And of course, this simplifies to V naught equals V max. So we're left with a situation where the rate is not dependent on the concentration of substrate at all. So this looks like rate equals K times the concentration of substrate to the 0th power. So it's a 0th order reaction. So when we're way out here, this is 0th order. The rate of the reaction is independent of concentrations. It's only dependent on the rate constant, or in this case, Vmax. So under these conditions, it's a 0th order reaction. In the next video, we're going to explore Michaelis-Menten kinetics a little bit more. We're going to take these two terms, Vmax and Km, and convert them into something that's truly useful for comparison with other enzymes.